Part 5 is on page 125 of your lab manual. Now we're seeing a normally passing valve, which always goes by the same name, the pressure reducing valve. Its main purpose is to reduce pressure downstream. The reason for this is reducing the output force of actuators, as in a clamping circuit. In some applications, clamping cylinders do not use full system pressure because it would cause them in turn to damage the part being clamped. Therefore, we manage the downstream pressure by the use of a pressure reducing valve. So the valve is normally passing. When pressure downstream exceeds its spring limit, then the valve closes. So in this illustration right here, we would see that on startup, with a low setting, that valve would be open. Then as we increase the pressure downstream, which is done mainly by the needle valve, we would see a backup on gauge B. When gauge B reaches the closing pressure of the reducing valve, well, then it would just simply close. And when it does, we would see that gauge A reads whatever the relief valve is set at. Part 6 appears on page 127 of your lab manual. In this circuit, we're using the sequence valve, and we're going to control it by controlling the drain port. The way that this valve has been designed is that unless the drain port, port number 3 at the top of the valve, has a connection back to the tank, that valve will not open. So if we're looking at either the sequence valve or the pressure reducing valve, port 3 must be connected to tank, or the valve will stay stuck in its normal position, which means the sequence valve stays closed, the reducing valve stays open. So in this illustration, we will use a remote method of controlling the sequence valve. Regardless of what the spring tension is set at, the RSDC sequence valve will not open until a connective path has been made by pushing in on the DCV lever. So unless we push in on the DCV lever, we will not see flow on the flow meter. Now, the sequence valve may be at its lowest setting, the knob that is backed all the way out, yet it will not open until we provide that path. You would also notice that the valve opens a lot faster than it closes. There's typically a 2 to 3 second delay of closing once the lever is released. The reason for that is the time required for the pressures to balance and then the bias spring to push the main stage closed. Part 7 is on page 128 of your lab manual. In this circuit right here, we'll demonstrate basic clamping operation using a reducing valve. A couple things to notice on this circuit. There's a needle valve placed in the line between the tank port and the return manifold. That provides back pressure on the cylinder whether it's extending or retracting. The instructions tell you to label the DCV according to the rule that you learned in chapter 3. So when you look at this DCV, based on that rule, you should know which of the ports are marked, where the P port is, the T port, the A and the B port. Another thing to notice too are the port markings on the pressure reducing valve. Notice that the inlet port is marked number 2 and the outlet port is marked number 1. Earlier I explained why this was, but Sun Hydraulic Corporation uses the same valve cavity for many different valves. And we still need to have a check valve around this valve because at the lower settings, any buildup of pressure on port number 1 can cause the valve to close, and this experiment will actually demonstrate that. So what you'll notice is at the lower values on gauge B, the valve tends to close and the actuator will stop moving. At the higher settings, we have higher readings on gauge B and slightly quicker movement of the small bore cylinder because the valve is opening and staying open at a larger amount. That is, more flow will go through the valve at the higher settings and less at the lower settings. So the purpose of the check valve is so when oil is coming from the actuator, from the cap end, attempting to get around this valve, there's little pressure buildup possible on port number 1. And so the majority of the oil flow goes around the valve back through the DCV toward the tank. You'll notice too that when you adjust this valve, regardless of what gauge A reads, gauge B can set at whatever value you wish. So in making the adjustment, you would push in on the lever. While holding in on the lever, you would simply adjust the valve to whatever desired pressure you want on gauge B, and that's the pressure that the valve will control at. So no matter what, if you set that valve at 200 psi, the highest value on gauge B will be 200 psi through any part of the operating cycle. Part 8 on page 131 is the operational test of a counterbalance valve. The counterbalance valve is the most practical choice for all load holding circuits. The operation of the counterbalance valve is that it uses two pressure values, one at the inlet port and another at the pilot port, to control its movement. If a regular sequence valve or pressure control valve were used to control a load, we would notice that it would hold the load at whatever its spring tension is set at, but it would also require that much pressure to open up, which might cause a delay in movement. The way that this valve operates is that the value of port number 1, which is the spring setting, is always going to be higher than the value at port number 3, which is the one required to open it up. Or in other words, port 3, the pilot, external pilot, is not activated until the operator wants the valve to open up. So in this particular circuit, what we're going to do is we're going to set this valve at a certain value. Then, using the relief valve, we're going to increase the pressure value at port number 1, and we're going to observe at what pressure the valve opens up. Minimum operating pressure on this valve is supposed to be 200 psi, but in practice we found it to be anywhere between 165 and 185 psi, meaning that the least that we can set this valve at, with the knob backed all the way out, or in this case the set screw, there is no knob, what we're going to see is that the pressure required to open this valve will be at least somewhere between 165 and 200 psi. In addition to this, we're going to notice that the value at port number 3, regardless of where the spring tension is set, will be in the neighborhood of 3 times less than whatever the set pressure is. If, for example, the set pressure on port number 1 were 900 pounds, then the pressure required to open the valve would be about 300 pounds. This is to get the valve to open up and prevent a delay of movement. Part 9 appears on page 133. This is an actual load holding circuit. A few things about the circuit before we explain what's going to happen. Notice that there's a component enclosure around the counterbalance valve, and that part of the symbology includes a check valve. That tells us that the check valve is actually built in, that is part of the main body of this valve. Now, in the circuit, the load is the spring. So we will actually compress the spring using the actuator. The spring will push back on the actuator, and that pressure which is generated at the cap end, which could be the weight of a vehicle, say a boom truck with deployed outriggers, can be substantially high, and we have to control its movement. So in order to provide this, we've placed the counterbalance valve in series between the cap end of the actuator and the actuator port of the DCV, in this case actuator port A. This of course is a float center DCV, and we're using this float center to our advantage because it does provide a path, in this case here, for venting the rod end of the cylinder when need be. We also have a T-fitting connecting a line to the pilot passage, port number 3. So at any time we want to allow the spring to decompress, oil which is being sent toward the rod end of the cylinder will simultaneously be sent toward the pilot passage. So what generally happens is that when we release the spring, we will do so in a controlled manner. Without control, the spring could run the cam back against the cylinder and move so quickly it could cause machine damage. So when we say control the load, this is really what we're talking about. Complete control of the load at movement, speed and velocity that we would consider to be acceptable for the machine and for the operation. Okay, so you also notice here there is a flow control valve connected from this T-fitting connected to the cap end, running back to the return manifold. That flow control is used for an emergency situation. Should oil be trapped on this end of the cylinder for any reason, that is our emergency bleed off. We're demonstrating here how you can adjust this valve, although the manufacturer often will tell or say that there are no in-field service adjustments. The valve could be serviced if the technician understood its operating principle. In most cases, a quick troubleshooting approach is made where if they see oil leaking around the rod of a cylinder that has a counterbalance valve on it, they assume that the cylinder is bad and they replace it. If the cylinder is giving way and we don't see oil leaking from the rod, typically they will say replace the counterbalance valve. It is true that in most cases it's either the counterbalance valve which has failed or the cylinder itself. It is rarely needed to adjust these valves in the field, but after performing this experiment you could actually do that if you chose to. I went through these circuits rather quick. I would ask that you take a look at each one of the experiments, and if you have any questions about anything that I said or anything that's in the experiment, it's likely I may have missed something, then please send those to me through email and I'll get an answer back to you as quickly as possible.